some problem, extremely tempting, because you probably heard the saying, greed is good, by Michael Douglas in the movie Wall Street from 1987. Actually a good movie. And of course, Mr. Burns, of course, right? Who also was quite greedy, still greedy, right? So as we look up at these personages, of course, as we know, there are some downsides to greed. So we shall see that in terms of algorithms, there are serious downsides to this greedy approach. And the downside is basically this: it rarely ever works. The greedy approach, when it works, it's amazing, right? But it's very rare, actually. There are specific conditions for this greedy approach to work. And you might be asking now, of course, what is the greedy approach? So greed meaning is, so I would call it myopic, meaning you look only close by to your solution. Basically, you don't look at the big picture. You take a very short-sighted view of the problem, basically. So let's illustrate with this example, right? So basic idea is this: you make a greedy choice, and then you go to the, again, reduce the problem to a sub-problem of the same problem. So probably you could solve this involving something recursion or something like that, and you repeat. So it is approach to solve a problem, a heuristic, a rule, right? So you make a locally optimal choice, right? You only look what's good for today, or maybe what's good for tomorrow, but not what's good for next year. So here's an approach. So this is a greedy algorithm. We want to find a path which gives you the highest sum, right? You have tree-type data structure, right? We'll talk more about trees, of course. So if you take a greedy approach, what would be the greedy approach here? The myopic meaning short-sighted view would be you always take the largest value, right? So you take this path. You start at the top, 7, and of course, here trying to find the biggest sum, the biggest increase, or not increase, but biggest sum here is, of course, you take 7, you take 12, right? Because it's the biggest. You don't know the big picture. And you take 6. And of course, as you can clearly see here, that is not the right answer. That is not the optimal answer, right? The answer, of course, lay behind here. So this type of problem, you just imagine you have a huge tree, right? It's impossible to use a greedy approach here because you don't know where the big value is. Maybe there's 100 million somewhere. Like you have maybe, 0, 0, minus 5, minus 5. At the end, there's like 100 million somewhere, right? And that's the path you need to take, but you don't know that, right? If you take a greedy approach, right, you will not get that path, right? So that's the essence, the problem, and also the appeal of the greedy approach, right? Because if you have a huge search space, greedy algorithm doesn't take much memory, right? It's very relatively easy to write. You just come up with some rule, and you sort of like go. You go and you solve it. But of course, then the question is, of course, whether this actually was the optimal. So greedy approach might be okay if you just need some answer, right? So greedy approach in this case, is this guaranteed to be, well, it's probably not going to give you the worst answer, probably, right? Assuming, well, of course, let's look at this. Let's think about this. Is this, well, it guarantees you an answer in this case, right? However, if there is no 5 here, you could probably end up with the worst, the worst case, the worst solution. It would be a solution, it could be theoretically the worst one, right? It was very tempting, but it led you astray, right? So that's basically the idea, right? So, okay, so now we go to a classical problem of changing coins. Maybe some of you have heard of it, right? So idea is this: you go to a coin change machine, or maybe you have a cashier, you're working cashier, right? And you want to minimize, that's what you're trying to do. You want to minimize the number of coins you return, right? Somebody gives you, paying you something, gives you like pays for something with, I don't know, somebody wants 36 cents, right? You need to give a change for 36 cents, right? So you give it 20, 10, right? This is a Europe, right? 5 and 1, right? No, that's a solution, right? So is this an optimal solution? Well, what do you think? Is it optimal? Of course, it's optimal, I think, again, with what provision? Assuming there's no 36-cent coins, right? And there's no 25-cent coins, right? We'll see, this is important, right? Assuming these are the only nominations we have, right? We don't have 50 cent doesn't work, right? So we have 20, 10, 5, and 1. so for this type of problem, so can you come up with a rule to with a rule, a heuristic we could use in our greedy algorithm? What would be the rule for giving change? Somebody wants 36 cents. How could we? What kind of? What would be our rule, right? Without peaking below, what would be the idea? Yeah, exactly. That's a simple greedy rule. Always give the biggest possible, right? So 50 we can give 20, and of course, and this is a simple example. We had only one of each, right? But if you give 20, we can maybe you have let's say 42, right? You give 20, you can still give another 20, right? And then you cannot give 10, you can give 5, you can give 1 and 1, right? And that also should be the optimal answer, right? So local, we always make this greedy choice of giving the biggest coin possible, right? So it seems extremely tempting, right? And I can give you a hint, it works well for European coins. Yes, and American coins too, right? But there we'll see there's some downsides again to this approach. But as far as Europe, right, and most of the world, this approach works perfectly. It's actually the optimal solution. So the greedy approach is one of the rare instances you can actually apply a greedy approach and solve it optimally, right? So let's see an example. So this is so your rule, we will use it. So this is an implementation in Python, a coin changer, right? We're going to show how much we want, and we have our denominations, right? And here, of course, I also supply the euro, 2 euros. We have 2 euros. Yeah, we have 2 euros, right? 5 euro banknote, and of course, you could apply more, 50 euros and 100 euros, right? These are in cent denominations, right? So we have a hash map, of course, dictionary, right? Initialize with 0, right? All denominations, and then we sort the keys, right? For C and sorted coins keys, right? So we go in reverse order, right? We sort the keys, right? And we start with this one, right? We start in the reverse order, like, because that's where we start. So we check. So importantly, so we check. So we sort the keys of the coins in reverse order because our greedy rule specifies that we should try the biggest denomination. You know, I guess coinage denomination is actually for banknotes. I don't know how in English you say for coins. Maybe I don't know, nominals. I don't know. Right? Available. Right? First, right? So what rule do we apply? So here, notice something here. So we add, right? So look at this part here, right? So cents divided. So what do these two divisions mean? What is that? Remember in Python, some of you know Python, right? So two divisions means it is evenly, right? Without it's without reminder, right? You get integer value. It's an integer division, right? So this means you will get exactly. So this part here is how many of the current denomination you can fit into. You know, so you have 40, right? You'll fit 20s, right? If you have 45, you will still fit 2 20s, right? And you have 5 left over, and that's the part here, right? This is the part here where we will see actually the reminder, because you might have something remaining, right? So, and now, of course, what we do is eventually, hopefully, of course, this depends on what kind of coins we give, right? Eventually, right? Eventually, provided we have I guess current one unit coin, right? In our denominations, we should reach no cents left, right? No cents left, right? Nothing will remain, right? Because eventually we'll divide. Let's say we have 4 cents left. We have 1, right? So 4 divided by 1 will be, of course, 4. So it means we have 4 ones left, of course. So let's test this. Do I have it actually here, right? So let's test this coin changer. Yeah, of course, I trust myself, right? And let's see if it works, right? So I have 100 cents, right? kind of silly example. Of course, in this case, it gives you answer is 1, right? Because of course you pass it 100 cents, and it will give you €1, right? Just €1, right? Change. So 98 cents. So what should be 50 for 2 20s, 1 5, and 3 1s, right? To me? All right. Good point, because we have 2-cent coins, right? So actually, yeah, 2 and 1, exactly. So let's take a look. Indeed. Let's see. Or did I do wrong? So why is it actually? Because I didn't pass 2s?
Yeah, there's no 2s.
Right. So, but we have 2s. We have 2-cent coins, right? Let's do that. So let's do that, right? Right. So let's do that. Yeah, of course. Pick up my wallet, but of course we know there's talk of getting rid of 1-cent coins and maybe even 2-cent coins, right? So let's do it again. So now, of course, since you have a 2-cent coin, it will be your answer, right? So 5 2 1, right? 2 20s, right? 150, right? Cent, right? So it works great. We can do some bigger denominations, of course, again, 377, right? So 22, €2 coin, €1 coin, right? 550. So looks correct, right? So no ones, because of course 5 and 2, right? So again, we can do one more, right? Some bigger, right? It will work as long as you provide the correct denominator. So, but of course, the problem is now, how do we? Is this actually always the right approach? This greedy approach? And it seems it's very tempting, right? So I'll give you a counter example. But the good news for you is it's not in European money. But I'll give you this weird denomination: 1 7 10. So you have a 7-cent coin, right? You have 10-cent coin. You see the problem here already, maybe, right? And I want change for 15. Yeah. So what will happen? The greedy approach will do what?
Take the 10 and mark 1.
Yes, but in this case, that's not the correct answer. It's not the optimal answer. Why? Because we could have 2 7s and 1. So we've got only 3 coins instead of 6 coins, right? So let's take a look. So this is so greedy approach will give me 6 coins, right? But we can see, of course, that's not the correct answer. So here again, 6 coins, right? Even here it still fails, right? 1 6 10, it still fails. It'll be 2 6 and 3 1s would be 5 coins, right? So there is a downside. So it's not optimal, right? So a hypothesis, and this actually would be interesting, maybe some of these theses or something. What's the threshold for when does it start failing? Actually, it seems like you need the next one, like it overlaps, right? The 7 and 6 coin overlaps the 10 coin, right? So that is sort of like a condition where your greedy approach will start failing, right? Because there might be some situations where these slightly smaller coins could be more optimal, right? So you see the problem, right? So the greedy is not, again, greed is not always good. So our question might be, actually, is there actually a country which has this type of problem? Well, if you think about it, some countries, somebody gave me some examples, actually, some island countries somewhere in Micronesia somewhere. But basically, if you have a 20-cent coin or 25-cent coin, you run into this problem, actually, right? So let's say if you have 40 cents and you have 20 cents to 20 cents and a 25-cent coin, and let's say 1 cent, right? It will give you a really bad answer. It'll give you 125 and 15 ones, right? Instead of 2 20s, right? Trivial example, but that's something actually real life example. Sometimes there is some countries, like when there's a maybe money change or something, right? You have a 25 and 20-cent coin, actually, right? And that's actually
smaller one has to be at least half of the next larger.
Yeah, that seems to be but it's just a hypothesis. I think I think it can be proven, right? Actually, that is a necessary condition for this greedy rule to fail. I'm sure maybe somebody can find actually, maybe there's a literature on this actually more. Right, let's see, why do we have? Oh no, I just don't see this. I don't want that. No, it's alive. It's alive. It's still alive. Right. So much like hypothesis, but it's not proven, of course, right? So it should be less than twice. So Soviet rubles, actually 135, 10, 25. This is from Soviet times. In this case, it doesn't really. There's no problem, right? Why? Because 2 3s, right, and 1 and 5, same thing, actually, right? So it doesn't really break the situation, actually, in this case, actually, right? So, but if you had a 20, that would break. So in this case, this is sort of like it's not completely that hypothesis is not quite in here. It doesn't really match, right? So because you have 1 and 5, right? It's same as 2, 3. So actually, there's no problem here in this changer, right? So 4 cents, right? We can try for some more changes, right? So with this easy example under the belt, maybe somebody has some questions on this approach, maybe in any chat, right? All right. So.
Well, what if you had a 9 in the 1, 3, and 5 example?
Okay. So 9.
5, 1, 1, 1, 1. What if you have 3, 3, 3 otherwise?
Okay. How much you want to change? 9 units? 9 cents?
Yeah, 9 cents.
And you have what? 135?
135. Yeah.
So 135 is same as 3 3s, right?
3,
3 3s is 135, same thing, right?
I guess, yeah.
Yeah, that's what I'm saying. It's the same thing. You get even, right? So I think it's a little bit the hypothesis. I think you need to modify this. I think the next 2 coins should maybe somehow match so the previous and the middle coin should be equal to the previous. 2 middle coins equal to the previous and the next, or something like that. There's some threshold, right? It'd be interesting to see actually what makes the rule. When does the greedy rule break, basically, right? So. Okay, so that of course the answer is, of course, it should be wherever if you cannot create a optimal problem from a smaller problem of the original problem, that's when a greedy rule will fail. Okay, so now let's move on to another famous example, very famous problem called knapsack problem, right? You're a traveler, you have airlines, 15 kilograms, of course, is actually not even very realistic. It's like 80 kilos on Air Baltic, right? So most airlines don't give you 15 kilograms, but let's imagine you have 15 kilo limit, right? And you want to bring some goodies, right, from your overseas trip. And there's a lot of variations of this, right? But you want to basically maximize, right? You want to maximize the value you bring back, right? Right. So I don't know, you're a courier or whatever, but basically, you want to bring the best things back, right? And here, best being most expensive, right? So what do you bring, right? You can bring 12 kilos of something which costs $4, right? You can bring something which costs $2, right? Something which costs $1, something costs $2, right? So notice, so of course, there are different weights, right? And of course, so different values. So here, of course, you cannot bring everything in this case, right? You have it's 16 kilos, right? So what should you bring, right? That's a good question now here. What can you bring back?
Best is the $2 1 kilogram all the way.
So, but of course, the question, okay, so there are different problems. So if you can only allow one of each, right? This is so-called 0-1 problem, right? This is the hardest one, actually, 0-1 problem. So what would be the rule, the greedy rule? What should be the greedy rule, first of all? You have the price, you have the weight. What should you do?
Take the most expensive thing first.
But okay, so, well, most expensive thing first. Yeah, if you go to what happens in Latvia, I said in America, in Latvia, in European regulations, if you go to a supermarket, what do they have underneath? They have price per kilo, right? So we should try to do the same thing. I think that would be better rule. If you just get the most expensive thing here, right? We can run into that should not work. This, I mean, it's a valid greedy rule. I mean, you can apply it, right? You can make a greedy algorithm which takes the most expensive first without looking at the weight, right? So you can see how easy it would be end up in a at a really bad situation, right? You take the most expensive thing, but it's actually very heavy, right? And you could have instead gotten like 6, 7 slightly cheaper things which are much easier, much. Yes, we need to get the price for the price per kilo in this case, right? Which is easy. We have the both data, so we divide. So we can calculate. So here it is 12 kilos. So it's I guess it depends how you calculate it. So it's 3 kilos per dollar, or 1/3 of a kilo per dollar. Yeah, I guess no, 1/4 of a kilo per dollar. Yeah. So divide 12. So yeah. So each dollar is 0.25, right? Each kilo costs you I mean, you get 1 kilo of weight gives you 0.25 cents of value, basically, right? Here you have dollar, right, per kilo, price per kilo, right? here you have $2 per kilo, and here you have also $1 per kilo, right? So these are equal actually, right? So now this leads to the question, what's the actual, in this particular case, 0,1 solution, right? What would be the optimal solution? If you get the best values here, right? These are the best values for sure, right? You see, right? These are, and assuming, okay, so this is the original problem. The hardest one is so-called 0,1 if you only have one item, right? So we pick 1, 2, 3, right? That's how much kilos? 3, 4 kilos, right? And what's the problem? We have 4 kilos in our knapsack or backpack, and we cannot legally put in the 12 kilos, by meaning somebody's gonna catch us. We'll have 16 kilos. We'll have to pay penalty, right? So, but this is $4, right? So that's not the so we 2, 2, 1 is 5, right? But instead, who can tell me the solution actually to this particular problem? The best, you want to get the most money, basically.
Green, gray, and
Yes, and
blue.
yeah. So because that's 12, 1, 2, that's 15, and 4, 2, 2, that's $8 together, right? So you put full backpack, and you bring back $8, right? That is the optimal solution. Of course, you can do this as brute. If you have only four items, you can do brute force, of course, right? You can check all different combinations, right, and no problem, right? But of course, this is actually a serious problem in logistics and in general, right? Oh, there's also another one. I forgot to mention this one. So this actually be better. That changes things completely. Right? That's $10 immediately, and that's a pretty good deal, right? That is what, 2.5 dollars per kilo, right? That's the best. You should take that one for sure, right? But then of course I think we can change it again. Then the question is, of course, can we do any? Then of course that makes, then you don't need the green one anymore. I think you take these ones then, right? That makes it easier, right? So this is a classic problem, right? But there will be variations, right? And again, so let's take a look. So 0,1 knapsack. So this is the hardest one actually, all right? And so if you do a greedy approach, right? So greedy approaches get values, right? So let's look at this example. We have weights 20, 50, 30, right? And values are 60, 100, 120, right? And capacity is 50, right? So, and we can only copy one, right? So we want to maximize the value, right? So greedy code, right? We have capacity, weights, and values, right? So we're going to initialize our knapsack, right? Or values. We're going to get the value by weight. That's what we talked about, right? That's what you have in supermarkets, right? So best bang for buck, right, in English. And we sort, right? We're going to sort. We're going to use lambda for the value, right? So basically, we're going to get the best value, right? And initialize this. And initially, we have a completely empty knapsack. And of course, we're going to put stuff inside until we reach balance, until we cannot put anything in, right, by the value, right? So we check, can we get the best value, right? If we can do it, we do it, right? And we adjust the weights, and if we reach capacity, we are finished, right? And that's it, right? And the question is this going to stop actually? Let's see. We put in, and we go through all. Okay, yeah, this is gonna early break, right? Because if we reach capacity, but then we're gonna try the other ones, right? We can keep trying, right? Maybe we get maybe we have something we can still put in, right? So it seems reasonable, right? So idea is, right? So we keep trying if we do not get the current best value in, right? Because maybe something else will fit. Maybe something else will fit, right? Again, sorted by value, best value. Right. Okay, so let's see if this works. So we return knapsack, total weight, total value. I should really rewrite this code using classes, because what I don't like about this code implementation is that the weights and values are in two different arrays, in two different lists, right? So they kind of, it's easy to lose them, right? But let's take a look at the simple example. Maybe we'll see this. So weights and values, I would have liked to do this in like class-based approach, have a item and weight and value inside the item, basically, something like that. But okay, simple implementation. So you give it capacity is 50, right? And we have these values, right? Then of course the solution is 2060, right? On 30, 120, we get the values 180, right? Because why? Because this is what? 4 units per weight, right? We can take $4 per weight, and this is $3 or 3 euros per weight. Let's use European money, right? On this one is only 2, right? So again, so we get the correct solution in this case, right? We have the greedy approach, very reasonable greedy approach, right? Best value, right? So, but unfortunately, right, it's not always the best one. So this is actually made up example again, but you see, we have weights 40, 32. Still, the capacity is 50, right? So this is let's calculate this. Let me give you the weights, like the values. So maybe you trust me on this, or maybe I'll do it afterward. Yeah, I'll do it here. Okay. So the solution, so the greedy approach gives us, we should take the 40, 70, right? 40 weight and 70 value, right? So we bring a 70. But you can see there's another solution here, right? Instead, if you took the next two values, 30 and 20 weight, that fills out the bag, and the total value would be 74, right? So this is not the best solution. So our greedy approach again has failed, right? It gave us a decent solution, very tempting solution, but it's not the best solution, right? So again, you can see this. So why did it happen? Because you can see the 1.75, that's the best value. This one is next best, right? And this is the third best, right? So again, so you can see again that the knapsack 0.1 knapsack actually cannot be solved in optimal way with the greedy approach. In fact, if you read about 0.1, in general case, it's actually a so-called NP-hard problem. It cannot be solved. It does not have a really full algorithm, because there's some improvements, some approaches, multiple approaches, right? But actually, it's not solvable easy. So if you don't have a 0.1, right, what can you do is, of course, let's imagine instead of like transporting hard items, we have like, I don't know, butter, or I don't know what else, butter, honey, I don't know what else is cuttable. What else can you, something which is divided, I don't know, gold. See, alcohol hard, it's like it'll, well, yeah, assuming you can divide it, right, and you can have smaller bottle. Okay, I guess you can go there. So fractional knapsack, right? So this is a different problem, because we are allowed to cut. We're allowed to cut, meaning we are allowed to change, we are allowed to move the item, and that's actually really, it makes the problem much easier actually, right? So we need to modify our original greedy approach. We still look for the best value, right? But now, what's the approach? If we are reaching the end, right? If you're filling out our backpack, what do? Yeah, the last one we cut. Like if we are reaching, if our current best value does not fit fully in the backpack, we just cut it off, and that's it, right? So this is like the perfect example of where greedy approach will work, actually. Like this is one of the rare examples where greedy approach is like just perfect, right? Because you always take the best value. That's our greedy rule. And if you reach the end, towards we have the end, right? We can cut, right? And then we'll always, and reason it works. Well, again, we'll test it, of course. We can test it, right? So knapsack fractional, same thing again. We saw everything stays the same except the last part. If you don't have, right? So this is a change. I changed this code a little bit. If we have allowed, right? So we actually do we basically cut. This is the part where we cut, right? If we still have, if you basically here we add everything fully, right? We add everything fully in this case. If you don't have enough room, right? We actually cut it here, right? We do a cut fraction, maybe around a couple digits. You know, that's just a technicality, right? And allows how much we want to add, and this will give us perfect solution, the optimal solution, right? So, right. So let's do same example, right? Still works, right? Because nothing changed, right? How about this one here, right? So 3050, right? So of course, in this is a trivial example, we only have one item, but we have capacity 10. So we need to cut it in 1/3, right? Yeah, 1/3. Yeah, 1/3, right? So how about this one here, 3020, right? Again, we can cut it. And how about the one yeah, so this example here, right? So this example, right? So what changed, of course, is a problem, right? The problem changed. We give it the best value as 4070, right? 40 weight and 70 value. And then we cut half of the second best value, which was 2034, and we get 87. And that's the optimal value here. And again, the reason we can prove this again, it's at any point, the solution to this problem will involve taking the suboptimal problem, basically the next sub problem, applying the same approach, basically, right? If you can prove it, probably using induction, that this works, that's how you would prove it, that actually is correct, right? Then you have a greedy solution on hand. But again, it's extremely rare again, so it's good for first estimation, right? So now you might think, okay, so here's the thing. This gives you another rule. We'll see this again in our algorithms. Sometimes it might be good. These problems are related 0, 1 and fractionals. They are kind of similar, right? But turns out 0, 1 is basically impossible to solve in general case optimally, but it's fractional perfectly. So what we can do, of course, is we can use something called relaxation. Sometimes we have a problem on hand in general, not only in abstract, just any problem. We can see maybe we can solve something slightly easier, right? We call this a relaxation, right? We relax, we solve, teacher gave me this hard problem, I'll solve something easier, right, instead. So if you choose this easy problem wisely, it can give you a very good approximation what the hard problem solution might be will look like. And also, you can sometimes use this to guide you towards the correct solution in a hard problem. You'll see this approach later on, actually, right? So if you can try to solve a different problem, but it's easier, right? So if you have something, I don't know, job interview or real life problem, and you don't know how to solve it, see, could I reduce this to something similar, but it's easier version? And what happens then, right? So that's one of the approaches here, right? So we solve the easy problem, right? Now, let's look one more problem. I think that's actually a bit. So this is a similar situation. It's called point cover interval problem. And again, you can dress it up as a class. Maybe you need to got maximum number of classes or maximum number of shopping stores or something like that, right? You need to find here. Okay, it's interval cover problem, right? So you have some intervals, right? And you want to cover points. So you want to cover points, basically, right? So let's see here. This actually might not be that good problem, but let's take a look. Yeah, so you have a bunch of intervals, right? And you want to cover minimum set of points. So you want to cover all intervals at least once, basically, right? You have a bunch of intervals somewhere on your some sort of time scale or some sort of linear scale, right? And you want to cover them all with minimum number of points, right? So not very, actually, I will maybe not cover too much time on this one, but the idea is this. We sort the intervals in increasing order, and if interval is not covered, we add this interval endpoint to the set of points, right? So we'll see this maybe an example. I should give you an example. So we have these intervals, right, on a linear scale, right? 2, 5, 1, 3, 3, 6, and we have -5, 5,000, like a big, huge interval, right? So which points would cover everything? And you can see the answer is 3, right? If you have assuming, and for this problem, we assume if it's endpoint, it still counts. Endpoint is included, right? So if you choose 3, it will cover all 4 intervals, right? It will cover 2 to 5, 1 to 3, 3 to 6, and obviously -5 to 5,000. 3 is an all, so that's solution, right? So how about this one? 4, 7, 1, 3, 2, 5, 5, 6. Unfortunately, here we need 2 points, right? We need at least 1, right? So we see here 4, 7, 1, 3, 2, 5, 5, 6, and 3 and 6. Is another solution? Maybe 3 and 7 would work, right? 3 and 6.5 would work, right? What else would work? I guess 3 or maybe 2.5. Yeah, 2.5 and 2.5 and 5.5 would work, right? So lots of solutions here, of course, right? So And I forget now, of course, what was actually real life application, but there's some real life problems where you could solve this, right? So here you have 1, 2, 5, 15, 14, 13, 15 again, 2, right, and 14, right? So the thing is, we sort by endpoints in ascending order, right? So the 4-point pairwise distinct I will not cover, but set cover. But there's one more problem: activity, the last one. I want to talk about the last one here today. So this is something maybe more applicable to you guys. So you can explore the other ones yourself. So set cover is also a similar activity selection, right? So you have a bunch of activities, again at linear scale, right? You can imagine them classes or courses, or I don't know, like I said, any activity, right? Or scheduling for computer computer course, for example, some job assignments, things like that, right? So you want to maximize the activities, and you cannot do two at once, right? A single core machine, for example, right? Or you just one human being, right? So we select, right? So how we need a greedy approach. Let's see if we want to solve this greedily. We can do this with earliest finish, right? So this actually, I usually do this, right? So there are multiple approaches we could take, right? But the only one actually will work here, right? So activity with the earliest finish, right? So that's the actual solution here. So we sort by the finish time, and this will solve it, right? So of course, you might be asking now, what's the complexity of this, right? Anytime you sort something, if you're using a normal sort, that's going to be, of course, n log n to start with, maybe something more, right? But here we have n log n step, right? That's n log n, right? Amount of activities, of course, right? And then iteration is linear, right? So do we have anything else here? Anything happening in the loop? Do we have anything that depends on a number of activities, right? I don't think so. No. Yeah, well, append is, you have to be careful. Sometimes it's append. If you have bad structure, appending sometimes could be take slow. But overall, this looks like n log n here on n, linearity here. So it's n log n because that's, they are separate activity, separate operations basically, right? So it's n log n here, this whole thing. So it's very efficient. So we'll supply some activities. So A 1 4, B, C, D, E, F, G. In fact, before earlier years, what happened? I had some good activities. Maybe it would be aerobics, and this would be basketball. This could be something else, and something else, and something else. And these could be times, basically, right? So, right. So it chooses most you can do. It's like if you go to some show or something, you want to do the most. You don't care about the long activity, right? You just want to squeeze as much different things in one day, basically, right? So again, maybe you don't want. Okay, I do have an example here. Yeah, here's an example. Yeah, art class. I made an. So you have this art class, band practice, chess club, and so on, right? And these will be the times, right? Assuming we start counting, a chess club meets from 0 to 6 at night or something, right? So, but yeah. So again, but that's the interesting thing is that we start with the end time, right? So why end time? Because that's when we start the next one. So if you start, this might not be the obvious first choice. You might think, okay, how about starting I should pick the activity which starts the earliest, right? That'd be very tempting, greedy choice, right? But you can see why it wouldn't work. Because you could choose some activity which starts at 0 and goes all day, right? And you sit in that class and you hate yourself, right? I could have done 4 other things during the time, right? You cannot leave. The teacher has locked the door, right? So starting point in this case would not be a good greedy. It would be a valid greedy algorithm. By the way, there's on a quiz today. There's a question I think where I asked for some choices. A bad greedy algorithm is still a greedy algorithm, right? It's just not optimal, right? So, I mean, you can come up with some weird. I mean, a greedy rule could be maybe just put finger in the wind and do a random check. I mean, it's still a greedy rule. It's just kind of stupid rule, but it's very short-sighted, right? But it's still it's a rule, right? So anytime you have a rule which does not look at the big picture, right? It just looks very short, whatever, like only around you, right? That will be a greedy approach here. So here this approach to look at the earliest stopping time is the correct one. Because another thing you could have done is look for the shortest activities first, right? That's also possible, right? But again, you could find some counterexamples. So one way of, it's easy to disprove greedy algorithms by finding counterexamples, right? If you can find a counterexample, you can say, okay, this is not optimal. Yeah, this is not optimal. It's much harder, of course, to prove it correct, because you seem, okay, it seems to work, and you can find a counterexample easily, right? But we saw with our coins, right? It works in general, it works for general coins, but it doesn't work for specific numbers of coins, right? So not so obvious. So here, let's continue this approach, right? So let's look at the, how could we should probably start with which ends first? Art class. You go to art class first, right? That ends first. Yeah, drama club and history club, right? And we finished by 11, right? So 3 activities. We can only squeeze in 3 activities here. Can we add one more, maybe? Right, I can do J, I, J. Let's do maybe, let's K. Let's start with K. Karate club, right? All right, and it will go maybe, I don't know, we can do like 16, 19, right? So of course this will be included, right? Yeah, so of course karate club is included, right? Of course, just double check, right? So now, so this is actually the actual real time, right? So real time, right? Again, we don't have to sort these activities these times, because again we are sorting by the second item. Again, technical issue here is of course that I am using, right, in our algorithm lambda, right? I'm using the second, sorry, not second, but third item, right? We have a tuple of 3 items: the name, start time, end time. We're sorting by the end time, right? So, and of course we will get some examples, right? Again, right? So no need to sort. And what do we get, right? So we print the activities, and these are actually, okay, we can do all of them. Yeah, we can do all of them. Let's see. Start at 7 o'clock. We go to art class, chess club, football, gymnastics, instrumental ensemble, and jazz band in the evening. Yeah, and we can do all of them, right? So 6 activities out of 9. So this is actually quite, again, for scheduling, right? Actually important algorithm, right? Even if you have many activities, you will find the optimal answer with this. Now, right? So one more approach on grid. If you want to hill climbing, of course, very applicable to artificial intelligence these days, right? So hill climbing algorithm. You are somewhere, right? You're standing up, right, and you can look in the distance, and you want to climb the highest mountain. What do? Right? Well, you look. The greedy approach is where the road goes up, right? You know, seems very tempting, right? So do you see this again? So this greedy approach, right? You have this function, right? You are here, right? You're somewhere here, right? And you climb until you reach so-called local maximum. It's a maximum, but the problem is with a greedy approach, you don't know if it's actually a global maximum, right? You have no way of knowing. You're stuck there, right? And then also you have other problems. Maybe you end up with this flat, like you reach this kind of plateau, right? You keep going, maybe then you fall off, but you won't fall off because you see, again, if you calculate the slope, the derivative, right? You call it is going down, right? Then you stop. But so this is of course a big problem if you have a unknown, the unknown space to explore, right? Maybe it's infinite, basically, right? Here you say, okay, how would I solve this? Maybe I'll make this smaller. I know I can maybe I'll make this in a new picture, in a new tab, right? Yeah, so yeah, like this. Okay, so greedy approach, you calculate the derivative, the short slope, next to, which way it goes up, and that's where you go, right? If you don't have, how could you solve this if you have finite space, right? You could just basically, go through and check every value, basically, right? If you have a finite space, you have 1,000 values, obviously you find the maximum, just go through all of them. But the issue is, of course, if this is continuous space, you don't know, right? Maybe there are big jumps, maybe there's, you cannot explore all possible values if you don't know the function, right? You don't know what gives you these answers, actually, right? So again, greedy approach here would be okay to start with, right? You will get some solution, you'll get some maximum, some local maximum, you'll find it, right? It just depends how deep you are, right? Maybe this local maximum is going to be very tiny, right? So what solution here? You don't really have a good solution in general. What you could do is, once you reach this maximum, maybe try jumping around a little bit. Maybe somewhere there's grass is greener. Maybe you do some sampling. Maybe you see somewhere else. That would be a discussion for another day. But yeah, you have some other things you can do. Something called simulated annealing, right? You sort of like jump first, like have a hot temperature. You jump, and then as you keep going, you stop jumping so much, and you settle down on a sump somewhere, right? And again, it is not guaranteed to give you the best solution, but you will find a solution, some solution, right? Okay, so again, hopefully this lecture showed you, I hope you are convinced that greedy approach is rarely the right answer. There are very few examples where it works perfectly, right? But if you have a problem, you don't have a solution to it, right? And maybe you have limited memory, you don't have many of the following solutions, many algorithms we'll be looking in this class afterwards will require you to use some memory for storing some calculations, some maybe caching something, pre-computing something. And if you don't have this luxury, you have you have an embedded device, maybe 4 kilobytes of memory, right, or something like that, then yeah, the greedy approach might be actually what you need, right? You'll generate some solution, because basically you're looking at some space, just by yourself, something's close by. Okay, so, and is that it actually? We so quickly finished. Let's see, we can finish, of course. There's 2 more we could look at, but I think I'll let you do this yourself. The activity selection set cover, very similar actually, right? Yeah, and again, but I don't see any very good practical example. Pairwise distinct summands also, right? So again, so if you encounter some problem and you see, okay, here's tempting, if you can find a rule to apply for a number of items, you have some heuristic you can apply, right? And then you know, okay, I can reduce to next smaller version of this problem, then yes, you can try a greedy approach. Just be prepared that it's not going to give you optimal solution, right? With very few exceptions. All right, I guess that will be all for today. If there are any questions, we can finish really early today. So maybe any questions? So if you need to give you a problem, you can come up with a greedy approach, right? Just figure out some rule, right? Even if it's stupid rule, right? You can try it and see, maybe you can come up with some good rules, of course. Yeah. All right, thank you very much. All right, I'll stop the recording and see you guys next week. All right, next week we will talk about, right, we will start moving beyond greed, right, and we will move on to dynamic programming, of course, where we will need some memory, we'll need some room for calculations, we'll be storing some results. So dynamic programming actually something is going to be applicable on your midterm, by the way, right? So of course, so all right, thank you everyone. So, varēs izsekot šodien, varēja saprast? Jā. Jā. Nu jā, vairāk nebūs šī kursā, nebūs vairāk nekādas smagas teorēmas, nebūs. Jā, būs vairāk šie likumi, šī piegājieni problēmām, kā atrisināt. Labi, jā. Tā. Paldies visiem, tiekamies pēc nedēļas. Uz to 25. martu? Tev bija kaut kas, tu man stāstīji kaut kas, tev bija? Mēs šeit runājam, es pilnīgi aizmirstu. Tad es vienīgais, man neviens neteica. Es tieši to mēs runājam pagājušajā nedēļā. Nu jā, es tos pagarināšu viņus 28. Jo problēma nav grūta, bet es domāju, bet tas neder, es pilnīgi piekrītu. Nav. Es ne, jā. Jā, protams, jā. Mēs pagarināsim termiņu pagarināšu midterm uz 28. martu. lai netraucē. Jā, labi. Jāpieliek klāt seju. Visu labu, visu labu. Cilvēki priecīgi, visu labu, visu labu. Tagad būs atkal klase, vai ne? Būs tagad jums te. Jā. Jā, tā, mums palika šis tam. Tā. Tur mums ir palicis šis te midterms, jā. Jā,